works. And then then we move on to about the ESI, the mass spectrometer using the ESI, and also using the atmospheric pressure chemical ionization. I think we can't stop here, right? We stop here about ESI. So I'm talking about ESI. The thing is, like you can see, is actually the particles, they get ionized, so they get charged in liquid state. In the liquid state, and then it has the nebulizing, and then the solvation. And then the like solvent evaporates, and then the charge density increase. And then when it has very high charge density, a high surface tension, and you have the Coulombic explosion, okay, because the same charge, the repulsion, okay, they have electrostatic repulsion. And then and the drawing gas that keep drawing it, they become the charged gas molecule and getting into the mass part. So in the electron spiralization, we see that. So it's actually, they got charged at atmospheric pressure. And then you have two pumps that further reduce the pressure, and eventually, in the mass spectrometer, it's had high vacuum, as you can see here. So that's why it has to move ions from solution to the gas. And then and during this process, because of the drawing gas and the heated chamber, so the solvent evaporated, right? And then the ions, your analyte got charged in the liquid state, in the aqueous phase, okay? In the liquid state, not really aqueous, depend on. And then they can't transfer from atmospheric pressure to vacuum. And then the yield ion beams with maximum current and minimum kinetic energy distribution. And so that's why we say that when you are using ESI, we can use some buffer or using some very small portion of acid, like say formic acid. So if you're using a positive electron spiralization, is help to make it charged, make it to protonated, okay? So promote the charge state, and then that will increase the sensitivity. At the same time, it's better. So if the solvent is more easier to evaporate, right? So that is more easy to transfer the ions in a solution, in a liquid state, to the gas state, okay? So to a gas phase. So that's why, if you are interested in certain compound, when you are using the solvent program, so we normally later on we will use some example to illustrate that. You'll see that it's better that if we elute it at a high organic portion, okay? So because that organic solvents, they're more easier to evaporate than water, okay? So, and that is for ESI and multi-charge that can make it possible to identify and quantify, determine very large molecules, okay? And then, we kind of move on to here, right? Okay, and this is where we stop, and then we're going to start from here, okay? And to focus, and then don't annoy by the, okay. So for this one is atmospheric pressure chemical ionization. So this is another soft ionization technique, so other than ESI. This one is atmospheric pressure chemical ionization. So which one is that chemical reagent that make the analyte get charged? So let's look at this one. You can see this is a little bit different. So from the ESI, first again, the eluent is coming out from the LC, okay? But however, once it comes out, you can see the nebulizer gas like blow in, and also the chamber is heated at 150 degrees C. So that means your compound, both the solvent, the gas, and this kind of gas flow, and also heat. So they desolvated. So they desolvated. That means they make the solvent evaporate. So desolvate the nebulize the droplets. So make both the solvent and analyte to become gas vapor. So they're just dry gas vapor. Okay. So dry gas vapors, I will just mute all of you, okay? And then then what happened is they're neutral at this moment. They're neutral, not charged. So how did they get charged? You can see here is the needle, and then a high voltage is applied at the tip of the needle. So that means now the ionization is not taking place in the liquid phase. So it's different from ESI. ESI is like, say, on the ionide, everything in the liquid phase, they got charged. No, now in APCI, so the ionization happened in the gas phase. In the gas phase, okay? So a high pressure about high charge apply on the tip. So you form a plasma or a corona, and then it's 6K volts. And then, so because of many of the solvent, the solvent vapor will be dominant, right? A lot of solvent vapor. And then, so many of the solvent vapor, they got charged, like this one, so protonated, they got charged, and then they can immediately transfer the charge to the analyte, neutral analyte gas vapor, okay, to gas molecule. And then because it is the charge, many of the charge is transferred from this charged solvent molecule to the analyte. So that's why we're beginning. So this even called the solvent mediated electron spray. And then so that's why it's called chemical ionization, because the chemical species that help to ionize the analyte now is the solvent, gas-phase solvent molecule, right? Okay, so that's the reason for that. And then so after that, so they get into the vacuum, and then so further, and from the, you see here is still atmospheric pressure, and get into vacuum and get mass spectrometer. Okay, and because of that one, you can see, because all the compounds, they need to be evaporated first. So if your compound is very polar, very long volatile, so they're not really suitable for this APCI. So that's why, so APCI is more suitable for the compound. So that is kind of volatile. That is some compound that is relatively non-polar, okay? Not that polar, because too polar, they cannot be evaporated so easily, right? Okay. And also, while you're doing, if you want to using an APCI as a mass spectrum, that's the interface, okay, for to connect the mass and also HPLC. So when you are running the HPLC, you do not want to use a very high level of the buffer, okay? So you want to keep the buffer, concentration of buffer or any acid or base that used to adjust pH to as low as possible. Why is that? Because like they need to evaporate. You see, so neutral compound and ionized compound, ions, neutral species, which one is more easily to evaporate it? Of course, the neutral compound, right? So that's why. So you want it to keep those buffer and ionics, so acid or base, so as low as possible, because you want to the analyte inside to be in a neutral state. Okay. So, and because of and also because the reagent ions, they are normally just protonated water, like show here, you can see here. Okay. So water cluster. So so that's why, so we also try to do to just keep those of the additive, those buffer as low as possible. And we also want to mention is both APCI and ESI, they are soft method. So because this protonation, so the mass spectrometer generated by either techniques, so they are still like typically dominated just by protonated, or if it's positive mode, or deprotonated molecules if it's negative mode. Okay, so and key part is like they're not suitable for very long volatile or thermolabile sample, because here you're heating at 150, and because here you evaporate those analyte, both the solvent, both the analyte into gas phase first. Okay, so and if you're looking for something very polar compound and also non-volatile, and you may want to use electron spray ionization, since both of them are just like soft ionization technique. Okay, so that's for that. And then so we finished talking about the detector, and then now we are going to talk about so more details about the chromatogram, and then so the factors that influence the separation efficiency of chromatogram. We can see here shows a chromatogram. So x-axis is retention time, right? Y-axis that is response, and then we measure the peak or height, so which is proportional to the quantity of analyte, and T0. So, and this is the, so this time for the solvent. to go through the column. Okay, also that is illusion time for the unretained peak. And then so, and if we're talking about the retention factor, if we talk about the K, okay? So how about for K1? K1 equal to what? K1 equal to, you still remember that? TR minus T0 divided by T0, right? So that is T R1 minus T0 divided by T0. That's K1. That's retention factor of compound 1, right? If it's compound 1. So if here is compound 2. And then the K2 is what? Is TR2 minus T0 divided by T0, right? Okay, so K1, K2, that indicate the retention factor. That means, like, say, how they can be retained by the column, right? The larger the K value, that means it has more solubility, or like more affinity to the column, right? Okay, and also when we are talking about, we want the two compounds like this one to be well separated. So when we look at the separation of peak 1, peak 2, we're using separation factor. We're using the alpha, right? Selectivity factor. So what is that alpha? What is alpha? Alpha equal to K2 over K1, right? So if alpha equal to 1, do you want that one? So that is not good, okay? So they're not separated, right? So that means our aim is what? When you do the separation, we want and the K value to be reasonable, because we don't want them to all come out very beginning, like say very short time, but not well separated. You don't want them to be like this one and very close to each other and not well separated. You don't want like that kind of peak, right? Okay, but you also don't want the K to be too long, because that takes forever for you to finish one injection. And then if you have multiple samples, and then it's too long, right? So we want the K value to be reasonable. Normally for the last one, we keep it to be about 10. So for K, for lost peak and soft value, if it's very complicated chromatogram, so and the range of those, the K value for all these species can be like say 0.5 to 20. So, but we don't want to keep the K value to be too large. And then, so at the same time, so you want to have a reasonable, a good alpha for all of them, because you want them to be well separated. And we can see that if you want these two peaks to be well separated, so it's better that they are sharp and narrow peaks instead of flat and fat peak, right? Okay, if you're pretty flat and fat peaks, they will overlay and they will show up like this way. They'll show something like, say, show up like this one. They're not well separated, okay? And then we say it does not have a good separation. So that's why, so to achieve a good separation, we want the column efficiency to be good. We don't want the peak to be broad, okay? So what are the factors that really makes the peak broadening, okay? So the chromatograph peaks, actually, they're generally broadened by 3 thermodynamic and kinetic processes. So what are those processes? They're eddy diffusion, so longitudinal diffusion, and non-equilibrium mass transfer. Probably, so Dr. Wang may have mentioned a little bit about that one when he was talking about the Van Diemen's equation, right? But I think for his part, you should focus on the GC. And now, how about in LC? So it's the same factors that influence the liquid chromatography. Will that be different from those like in GC? So how about the situation in LC? So let's first look at the eddy diffusion. What is the eddy diffusion? Okay, so well, before we talk about that, let's know about all these things, because we have eddy diffusion, longitudinal diffusion, and non-equilibrium mass transfer. So the H, anyone still remember what is H? Plate height, right? Effective plate height. So the plate height equal to the total plate height equal to, so their contributions, so from all 3 factors. So all these 3 processes that contribute to the plate height. Do we want a large plate height or small plate height? They want it to be a small value, right? Okay, as small as possible. Why is that? Because n plate number equal to the length of column divided by h, right? So if we have small h, that means you have if small and then you have more plate number. And then remember, resolution is proportional to what? The square root of n number, right? So resolution of the column separation is really related to the square root of n number. That means the larger n number, the larger resolution, better resolution. So that means like if we have a smaller, we want it to be h to be small. If we have smaller h, then you have bigger n, and then you have better. If we have better n, and then you have better resolution, and then better efficiency, we call that. Okay, so that means our target is like we want to see how we can make this h small. That's the target. Okay, how to make it small. Okay, in this case, let's look at. So first, what is additive diffusion? How can we make additive diffusion small? So what is additive diffusion? Additive diffusion talks about, and you can see that when this one shows this what happened actually. So, and then you can see, so because we're talking about HPLC, so LC column is a packed column. What does that mean, packed column? It means inside the column we have those particles. That's why, remember we're talking about dp, the diameter of the packing particles. We have the particles. So that's silica gel particles that coated. If it's partition chromatography, it's chemically bonded with some liquid layers. So that was stationary phase, right? Okay, and then so do the separation. And then so they're packed particles, okay, column with those particles. So, and if the particles, they're not, say, uniformly packed, so it's possible some of the solute, some of the analyte, they just find an easy way to go through the column. They may go through the loosely packed part, not many resistance, like easily pass through, so they comes out first, okay? And then so some of this analyte may not be so lucky, so they might go through some pathway, so that is more difficult. So, and they may make some detour, okay? So it takes longer time for them to go through the column. So they comes out lost. Okay, so that's why even at very beginning, they all enter at the same time. But however, when it comes out, some comes out first. For those one who takes a shorter pathway or easy pathway, so it comes out first. For those like who happen to have the more difficult pathway, longer pathway comes last. And then so that caused the peak broadening, okay? So, and therefore we can see that effect of this additive diffusion can be related to what? Can be related to particle size geometry, okay? So the tightness of the packing and of the stationary phase. So we can use a mathematical equation to describe it. So equal to 2 lambda dp. Okay, so here we see something key parameter, dp. What does it mean? dp is the particle diameter. That's easy to think about it because we see the smaller the particle, more tightly it can packed, right? Okay, so because the bigger the particle, the more space between them, so it's not really easy to pack them so tightly. So that means the smaller the particle, and then so the less contribution of this additive diffusion, okay, to H, right? Okay, so and lambda is the packing factor. So we want the particle to be uniformly packed. So if we say, for example, now we have the column with the diameter equal to 5 micrometer. So we want then all the particles to have this 5 micrometer, so as possible, as much as possible, okay? So we don't want some to be 6, some to be 4, some to be 2, some to be 7, and then so this number will be very big if it's that case, okay? So we want them uniformly to have the same diameter, okay? And also nice shape, geometry shape, not something like square shape. No, that's not good. So that's why, so it relates to size, geometry, and how tightly they're packed, okay? So, and altogether 2 lambda dp, and then so that's makes the contribution of eddy diffusion to the effective plate height of the column. And we know that when dP decrease, and then so eddy diffusion contribution decrease, that help to reduce the plate height. That's what we want, okay? So, and this is show you more about it. So just using some figure to illustrate, because we say lambda depends on packing uniformity. That means like say you want the particles to have this very exact same size and column geometry. So it has value, so that is between 1 to 2, okay? So for a very good packed column, this lambda value is just like 0.5. And we can see that for bigger particle, so they have larger gap space like in between, and for smaller particle, and then so it has the smaller so spacing so between the two particles, and then so that's why so smaller dp, and then so smaller eddy diffusion, okay? So therefore we can minimize this contribution by careful packing of the column with small spherical particles. Okay, so the first turn done. Okay, now question. So, does capillary GC has this eddy diffusion? Answer A, yes. B, no. Okay, yes or no? Actually, you can directly say yes or no. Do you want to like response in the chat box? Does capillary GC has this eddy diffusion contribution? Does it? No, thank you. Very good. So why? Because capillary GC has packing particles? No, it's not. The stationary phase is coated on the inner wall of this capillary, right? There's no particles packed inside capillary GC. We're not talking about packed GC column. We're talking about capillary GC. So that's why this term does not play a role so in capillary GC, but it does do the contribution to the liquid chromatography. Okay, so good. Now let's move on to the second term. Second term is longitudinal diffusion. What is longitudinal diffusion? Okay, we can say diffusion, something longitudinal along the way. Okay, so this one actually the figure illustrates the band broadening by the longitudinal diffusion. So it is because this is a start point, okay? So it's a start point, but we know that the compound, they have the tendency to what? To diffuse from the most concentrated part to the diluted area around, right? Okay, and when the compound is passing through the column along the z, okay, so axis, so it's possible this to diffuse in all directions, right? So it's not just along z, it can do up and down and the other way. Okay, so that's why. So the longer time is spent in the column, the more it can diffuse. That means when time increase, and then so longitudinal diffusion should be like say more, right? Okay, and what else? And I said like say because the diffusion, so it should be related to diffusion coefficient as well. If it's a larger diffusion coefficient, that means like say more effect for this kind of diffusion, right? That's easy to understand, right? So they to that one. So this one contributes to broadening, increase with the amount of the spent column, and also and the larger the diffusion coefficient, the more so it can contribute, right? Okay, and this diffusion not only occur in the mobile phase, but to a much less extent as stationary phase as well. So again, does this non-diffusion coefficient diffusion contribution happen in gas chromatography as well? Yes or no again? Does this longitudinal diffusion happen in gas phase as well? Yes or no? Anyone can respond in the chat room? Answer yes, very good, thank you. So the reason for that is what? because what is the mobile phase? What is mobile phase in gas chromatography? Maybe we're not saying mobile phase, it's carrier gas, right? It's gas. And compared with liquid, actually, which one has a larger diffusion coefficient? Which one? Gas. Gas even have a larger diffusion coefficient than liquid, right? Okay, so we see that. Anyway, so now let's just see. It's because we just mentioned, because relate to the time that the compound to pass through the column, also relate to diffusion coefficient. So that's why we can write this contribution of longitudinal equation. So by this mathematical equation, so it's related to diffusion coefficient, which is on the numerator, right? Okay. So, and also mu, what is mu? Okay. Mu is average linear flow rate of the mobile phase. So now we can see that the longitudinal diffusion coefficient is inversely proportional to mu. The reason is because the higher speed, the higher linear flow rate, the shorter time is spent in the column, right? Because T equal to L, the length of column divided by mu, right? Okay, so if we have a larger mu, so you have a smaller T, and then so that means you spend less time, less contribution to the longitudinal diffusion. Okay, that's why. And dm diffusion coefficient of the solute species in the mobile phase. So the larger the diffusion coefficient, the higher contribution. And this one, the phi is the obstruction factor. It's the measurement of the hindrance to the free molecule diffusion caused by this packing particle. It's normally have that one. So it's a constant within certain range. So we just want to just pay attention. It's like, it's really related to dm and mu. And the larger diffusion coefficient, the larger contribution. So now think about capillary GC and LC again. Do you think which one has a much larger longitudinal diffusion? Which one has a larger one? GC, very good, thank you. So why is that? Because let's look at this one. Let's look at the diffusion coefficient of gas, supercritical fluid, and liquid. Okay, so for those who have taken the sample protrusion, you know this one, supercritical fluid. But now for those who haven't, so you may don't know, but that's okay. We just ignore the supercritical fluids so far. We just look at the gas. We have gas and liquid. We'll see. So the diffusion coefficient for gas is 10 to the minus 1 square centimeter per second. And diffusion coefficient for liquid is 10 to the minus 5th square centimeter per second. So that means the gas diffusion coefficient of gas is about 10,000 times larger than that for the liquid. Okay, so that means the diffusion coefficient, this one, that makes the longitudinal diffusion to be a very significant factor that contribute to the plate height in gas chromatography. But okay, when compared with gas chromatography, this term HL, so it's not so significant in liquid chromatography because the diffusion coefficient for liquid is much, much smaller than that of gas. So it often can be ignored in HPLC. Okay, so that is a second term. So how about the third factor? The third factor is called non-equilibrium mass transfer. What does that mean? That means, so because it's kept in the mobile phase, because separation based on what? Remember, separation based on what? On the distribution of the analyte between stationary phase and mobile phase, right? Okay, so when it's distributing that, I try to reach an equilibrium. Okay, and then, however, because keep like transferring diffuse into the liquid, diffuse the coating like liquid phase on the particle and diffuse into the mobile phase, and then so there's a resistance to this kind of mass transfer in both stationary phase and mobile phase. So that prevents the existence of instantaneous equilibrium. So, and that makes the increase of the plate height. So that contribute to this non-equilibrium mass transfer. So it actually happened in both stationary phase and mobile phase. Okay, so because of that, so under most of the practical condition, so this one, so the non-equilibrium mass transfer term is the dominant cause of the band broadening. So it's bigger, it's larger, so then the contribution from the eddy diffusion and also longitudinal diffusion. Okay, so and as we see, because your analyte need to diffuse into stationary phase, diffuse into the mobile phase, because it depends on distribution of it between stationary phase and mobile phase. So therefore, this HM turn happen in both stationary phase and mobile phase. Now let's look at so how we can in a stationary phase. So when we talk about in the stationary phase, because as we were talking about in a little bit more detail later on, we say for the LC, we mentioned a little bit already, right, last week. So there are two types of the LC. It can be absorptive, right? Absorption chromatography or partition chromatography. When absorption chromatography, most of the case, the stationary phase is solid. Okay, so it's a packed column with solid stationary phase. If that is the case, which is pretty rare, so in our modern day application, we still have the absorption, but most of our HPLC application right now are partition chromatography. Okay, so now, but if it's absorption chromatography, so this contribution, so from non-equilibrium mass transfer is related to, what is that, mu? Linear flow rate of the mobile phase, right? And also the mean thickness of the absorption layer and also desorption coefficient of the solute. Well, and how about if it's partition chromatography? Partition chromatography, we have a liquid layer stationary phase that coated here, and then analyze, just try to diffuse into the liquid layer and come out. And then, so it is related to the stationary phase film thickness square, and also the speed, mu, and also the diffusion coefficient of solute in the stationary phase. That makes sense. How to understand that? Because it try to reach equilibrium, right? Okay, so that means when the speed is slower, so when the speed decrease, so you have the slower speed. That means you have more time to pass through the corner. That means you have more time, the analyte will have more time at each point to reach the equilibrium, right? And then because it has more time to reach the equilibrium, that helps to reach the equilibrium, and then less contribution to this non-equilibrium mass transfer term, right? Okay. Oh, how about the DF? Because if I have a similar layer, if I have only this similar area, and then it will be faster for the analyte to diffuse into the stationary phase and reach equilibrium, right? Okay, because the CK1, if I have much CK1, if I say here and much CK1, it takes longer time for it to get in and diffuse out, right? Okay, so that means the thinner the stationary phase coating, and then so the easier for it to reach equilibrium, because less time, less distance it has to travel to diffuse in, right? Okay, and then so that's why. So and then so if we have a faster diffusion rate, of course, and then the faster it can reach the equilibrium. So that's why when ds increase, and then so this term decrease, right? Okay, so this one, so smaller df, lower speed, and so faster diffusion in the stationary phase can favor a smaller h, sorry, in the stationary phase. Okay, so easy to understand. So how about mobile phase? So that's stationary phase. Mobile phase. So mobile phase transfer may be divided into two categories. Okay, one is for the moving mobile phase. The other is a stagnant mobile phase. Why is that? Let's look at the moving mobile phase first. Remember, we say now we have packed okay, packed column. So there's some space here. The shaded space is the gap between the gap between those packed particles. And then your mobile phase is actually flow through, so the gap between the particles, right? Okay, so when it's flowing through, when the electrolytes, they're in the same flow path, so they may not move at the same speed. The reason for that is you can see that for those in the middle, here I will draw another particle, okay, also red, okay? So you can see here. For the those that in the middle, this one, so it has least resistance. It moves much rapidly than the one, so by the edge of the particle. Because what? Because those that move along the edge of the particle, the speed is slowed down by frictional forces, right? So this is the hydrodynamic flow, so of the solvent, of the mobile phase. So it has this one. The one in the middle moves faster, and then so the one so that come along and along the edge of the particle moves slower. So that's why it makes the one in the middle comes first, and then the one comes at edge comes out later. Easy to understand, right? Okay. So of course, if you think about this one, so again, so if it has larger particle, and then so the gap will be larger, right? And then the more difference between the middle and edge one means like if it has larger particles and they have larger gap, right? And then the difference between the middle and those by the side will be even bigger, right? Okay. So, and definitely this one is related to dp and velocity, of course, right? Let's see that the contribution of this moving mobile phase, so to effective plate height can be given by HMM. MM means moving mobile phase, okay? So it's related to the square of the dp, particle diameter. As just mentioned, larger dp, larger gap, and then more difference between the middle and the edge. And then about speed as well. Why is that? Again, because if it's slower speed, and then it'll be more time, so that it will take more time for the mobile phase to pass through the column, and then so will be more time for the analyte to try to diffuse. Like for example, because at the same time you analyze their diffusion, right? So because here's faster and here lower, and but they can diffuse like happening at the same time. That kind of like say offset this kind of hydrodynamic fluid influence. So if it's longer time and more kinds of like diffusion can happen, can offset this kind of the effect, and then so that will be better, less contribution of this moving mobile phase time, right? Okay, so that's why mu, smaller mu, longer time for this diffusion happen to make it say to be say equilibrium, to be similar, and then so that's why. So if we have larger diffusion coefficient dm, and then so and more for those analytes, they can diffuse among different regions, and then to kind of offset, so try to offset this kind of hydrodynamic flow influence. Okay, so that's the reason. So it's dp again, this one dp, if smaller dp, if smaller mu, if larger dm, so and that can cause hm decrease, right? Okay, so again, we like what? Smaller dp. Does that recall to you the first term? The added diffusion. How about added diffusion? For added diffusion, do we like a big dp or a small dp? A small dp as well, right? Okay, so same for here, for the moving mobile phase, smaller dp. Okay. So how about stagnant mobile phase? You might wonder, what do you mean stagnant mobile phase? Remember, so we have the supporting solid state, the silica particle, they are porous. They are porous. What does that mean? So that means the porous, that means those areas. So here's a pore, okay? The pores area, they may filled with some mobile phase. then the mobile phase here will be at rest. Okay, they're not really exchanging or moving that. So they call that stagnant. That means not moving, not moving. Okay. So, and so there's very little interchange between the stagnant mobile phase contained in the pores and the moving mobile phase in outside pores. But however, your analyte, when it's passing through the colon, it's possible. So it can diffuse in and diffuse out, right? So, and some of the solute, so they will have to diffuse into the stagnant region because porous and the diffuse out. And then, so that takes time for them to reach equilibrium, right? So some of the solute particle, they may diffuse deeper, like this one, into the stagnant pore. Some may diffuse like shallow, like just a little bit into the pore. And which one will take a longer time to come out? Of course, the one that gets into the deeper, this one. So we'll be left behind and will be the one comes out later, right? So when they finally rejoin the mainstream or mobile phase, and then that can cause the peak broadening. Okay, that's the reason for that. Again, so this is easy to understand. We can also estimate, so the HMS. So here is mobile phase, stagnant mobile phase. Okay, M is mobile phase. And then it's again relate to dP. So this one, so a square. And then mu, again, this relate to the time because if like say the more time, so can they have to reach equilibrium if the velocity decrease, right? Okay, so and also because of dP, we can see the dP because of the channels to which the mobile phase flow through are narrow. So that's why. So the solute molecule, they do not have to travel really far so to reach the stationary phase. So that's why. So again, so if you have small dP, and then so they can need to travel less to reach the stationary phase, that's better. And then dm again, so if it's larger diffusion coefficient, faster it can catch up with the mainstream, right? Okay, again, so this is smaller dP, smaller mu, and also big dm favor. I think so far you already have some sense about what can we do to decrease the overall H plate height, right? I think now you already have some sense. We already talked about all these parameters. You see that? So which term we have seen that from very beginning to now? dP. Packing particle diameter, right? Okay, dP. Remember last week we mentioned that. I say the modern development of HPLC, the major development or major improvement of HPLC. So in the past years is a dramatic decrease of the packing material. Okay, so dramatic decrease apart the diameter of the packing particle. When dP decreased, so from say 50 to 10 micrometer to 5 micrometer to 3 micrometer and eventually to UPLC, which is 1.7 micrometer, the efficiency of colon separation increased a lot. Now you see why. You see, when dP decreased, it decreased the contribution from eddy diffusion. It decreased the contribution from this non-equilibrium mass transfer to peak broadening, right? Okay, so that's why. So dP plays so important role. So about the efficiency of the colon separation. That's why we want smaller particles for the packing material. Okay, so we'll talk about that again, so later on. So, but now let's summarize what we have learned so far. So we can see, so we talk about different and diffusion. So now, band picture one. Now is the initial bandwidth. Ready, go. Okay, so start traveling all this analyte. So first diffusion we talk about eddy diffusion. So some lucky ones go through the easy way, some very unlucky ones go through the more difficult way. So the left behind, and this guy is very lucky, so go through faster. So, and this one got the band broadening, okay, for eddy diffusion. And this is really related to what? dP and lambda, right? dp. Okay, so we like the smaller dp. And then now, so it's go to the longitudinal diffusion. But however, we say that for the HPLC, the diffusion coefficient for liquid is much smaller than the gas phase. So that's why this term, the second term, the longitudinal diffusion is often ignored in HPLC. Now we move on to a third term, which is the non-equilibrium mass transfer contribution. And then because the non-equilibrium mass transfer happened in both stationary phase and mobile phase, so that's why we need to look at both of them. So first, let's look at the moving mobile phase. And because it's hydrodynamic, so flow pattern, the one in the middle flows much faster than the ones like flow on the edge of those particles, because those ones, so they're kind of held back by the frictional forces, right? Okay, so and then so this is called peak broadening, HM. And then also has the stagnant mobile phase. So some travel deeper than the others. For those travel deeper, it takes longer time for them to come out and catch the mainstream. So, and therefore that also causes some broadening, that is stagnant mobile phase. And also for partition chromatography, a thin layer of the film, so it's coated on the surface of the porous silica particle. And then again, so the analyte also can diffuse into the coated or chemically bound stationary phase and diffuse out. And then some diffuse more deeper, some diffuse like less, and then so this stationary phase contribution for big broadening. So overall, we can sum it up, okay? So I think now don't be so, like say, don't be scared, because now I think you should be very clear in your mind right now, okay? So we talk about anti-diffusion, longitudinal diffusion, non-equilibrium mass transfer, which is HE, HL, and HM. And HE, which is 2 lambda dp related to dp, very important. And HL, which is dm and mu, but however, for HPLC, we can ignore that, okay? And for the mobile, the non-equilibrium mass transfer, we can go stationary phase and mobile phase. A stationary phase for partition, so this one, but actually more contribution from the mobile phase. For the mobile phase, all of them, we can see both terms not really moving, and also the stagnant relate to dp particle square particle mu dm. And again, so here we see dp again, okay? And here we see the mu, so here, okay? So on the numerator, and here, even we ignore that, but you see, the mu is here on the denominator, right? Okay, so if you want to write in the Van Dimster equation, because now you have the mu here, so the A term is actually the eddy diffusion contribution. So A term, so that means A term is proportional related to dp, okay? So the B term is B over mu. So the B term now is related to the diffusion coefficient, but it can be ignored in LC, okay? In LC, ignored, packed call. And then, so we have the C term. C term, we have it. So if this one is also the stationary phase here, okay? Also has the mu. So both the stationary phase and the mobile phase, so they all relate to C times velocity. And then we can see that for the mobile phase, it's related to what? Related to dp square dm, okay? dp everywhere, right? Okay, so that is how. So this one related to the Van Dimster equation. Let's take a look. So if we take a look here, because now the B term, so it's much smaller than GC. So when compare with the GC, and then that's such a plate height is smaller, okay, in HPLC, the plate height is smaller. And then, so the optimized speed actually also much smaller than than GC. If it's capital GC somewhere here, okay, just like here. So, and maybe even higher this way, if it's like this figure, just like to illustrate. So, and then so now we can see the H equal to is A, B, C. Okay, and now what do you see? This is a linear velocity, right? And then for HPLC, it's optimized almost equal to 1 millimeter per second. That is pretty slow, right? Okay, just remember the speed for GC. Okay, so this is very slow speed, right? It's very slow speed. So we'll see that. Okay, but anyway, so we see that is so, and for so therefore for when compare the HPLC to the capillary GC, and then so it has smaller plate height because this term totally ignored. Okay, and because this B value in GC is 10,000 times larger so than the LC, okay? And then so also the optimized flow rate is much smaller than GC as well. Okay, so if we do the comparison of so the packed column GC and HPLC, so we can see that so if it's for packed column GC and LC, and then you can see like for HPLC, term 1 important, term 3, term 4, term 5, so that's significant. Term 2 is insignificant because of DN. Okay, so how about I say, do not say packed column. How about we say capillary? How about the capillary column? So which term is important? Which term? So for capillary column, so that means terms, which one? Term 1 important? Is this one important for capillary? No, you already mentioned that. How about term 2? Right, term 2 important. What else? And which one? And also, so term 4, right? It does not really have a stagnant mobile phase, right? So it's not really porous, it's coated in the wall, okay? And then probably 3 may be important, but may not be that important. Okay, the most important should be these 2 actually, because the capillary column, they are narrow bone tube, okay? So they have the stationary phase, we say coated on the inner wall. So that's why it has no term 1, because no packed material, so no packing material, okay? So then that's why they have, that's why also, so the non-equilibrium mass transfer in the stationary phase is not really significant because of what? Because the film thickness, if you still remember, what is the film thickness of GC? About 0.1 to 0.5 micrometer, right? So the coating, the film thickness is about that, very, very thin. So it's very thin. So that's why, and also it does not have a stagnant mobile phase. So the 2 terms that's most important is actually the longitudinal diffusion and also so the moving mobile phase. That is for the capillary GC, okay? But however, for HPLC, we have term 1, term 3, term 4, and term 5. So, okay. So that's as you can see. So for LC, they show so much smaller H. Okay. So and also it has more flatter part for the C term contribution. It has slow rise of H. Okay, because that means what? That means later on you can see, although the optimized flow rate of liquid chromatography is quite small. So, but because there's a low rise, very slow, small slope here for the increase of the velocity, so the plate height with the flow rate. So that's why. So in practically people use at least the double of the theoretical optimized flow rate. So in a real analysis, even that, so it will not really influence or increase H that much. Okay, So it means the flow rate of mobile phase. So it's not really so important. And then so practically we can using a higher flow rate than mu optimized calculated theoretically. Okay, so that is for this part. Okay, so how about we take a 5 minutes break now? So we come back at 20:05. I think that's enough for you to take a break right now. Okay, so.
Recording stopped.